our next presentation is Graham Coulson and Helena Bender, Thinking Critically, Developing and Testing Technology to Mitigate Wildlife Vehicle Collisions.
Thanks, Rodney, and for the invitation to talk at the symposium. And hello to those of you joining online, particularly those of you who are in different time zones and are staying up very, very late. We appreciate you being here and joining in. I'd like to extend my acknowledgement of country to the Gadigal people of the Eora Nation, and note that they exchanged materials and information along huge trading routes across Australia, most of which have actually been built over by roads. And they didn't have vehicles, of course, but they also, and as a result, didn't produce the poor outcomes for wildlife drivers and vehicles that we're discussing today. But I think it would be really great to be able to think about how we can work towards not having those kinds of impacts into the future, which I hope might come out of our many discussions. So here I have 5 examples of technologies that are deployed to reduce wildlife vehicle collisions. And in each case, the evidence suggests the effectiveness is limited. So that's the orange color, and or negligible, that's the red color. And in the first part of the presentation, I'm going to use communication theory to highlight key considerations for integrating technology for addressing the challenges of wildlife vehicle collisions. And in the second part, my colleague Graham will discuss the importance of experimental design to be confident that the technology is having the desired effect. So here I've visually represented the transmission model discussed in communication theory. This theory is more commonly used for human communication, but aligns with signal detection theory, which is used for studying animal behavior, and information theory used in computing. Now, there are 3 key parts of the communication system. So we have the sender, which you can see in the top in the center there, and this is the technology, or sometimes the organism, sending the information, and that might be light, it might be sound, or it might be data. Secondly, we have the message or the transmission, which is at the bottom of the system there, and is the form of the information and its movement through the landscape from the sender to the receiver. And then thirdly, we have the receiver, which in this picture is our kangaroo, and it's the intended recipient of the information. So their sensitivities to the information need to be considered. Now, the response I've included here is not normally included in this system, but it's a really important component because it tells us whether the signal has had any impact on that receiver. If they don't respond, they didn't get it. If they do respond, well, it might have meaning, but it might not. It might just be a novel stimulus, as was flagged by Doug and Rob earlier. Now, I'm going to discuss each of these elements in more detail, and I'm going to predominantly use the shuru, which you saw earlier, as an example to expose where critical reflection would benefit other technologies being developed to address wildlife vehicle collisions. So thinking about the sender in the road context, the sender is used to reduce the wildlife vehicle collisions, is either usually mounted on the vehicles, like the shuru on the left, or it's installed along the road edges, like the virtual fence, which this animation comes from the virtual fence website. Now, the signals they send may be in the form of light, sound, or a combination of both. And I'd argue that decisions about what the best sender or technology should be should happen after all of the other aspects of the communication system have been explored. So if we turn to think about transmission, then the signals or the message that's being transmitted through the landscape will determine the area over which a receiver might be exposed to the information being emitted. Now, for a vehicle with a shuru, the manufacturer claims 400 meters out to the front and 50 meters to either side, and that's shown in that diagram at the left. Now, as reported in my PhD thesis quite a while ago, I took measurements of the first model of the shoe, which was the one I showed in the previous picture, with a sound pressure level meter in static conditions over bitumen, and showed quite a different transmission output. So that's shown at the right. So the shoe is located in the center of this diagram, with the speaker pointing towards the 0, and you're having the distance out in all directions being shown along those radial axes. Now, in the legend, you're having the sound pressure levels, which is an indication of how loud the signal is. And at 35 decibels, that's a quiet room, much like we're in today. If you look out the front, the 35 decibels is at 50 meters, which is an eighth of the distance of what the manufacturer is claiming. If you look out to the sides, the 35 decibels is occurring at about 30 meters, which is about half what's claimed. So trials on moving vehicles showed then that the signal could not even be detected above the noise of the vehicle. So lack of testing of signal and transmission still occurs even in scientific tests, such as Reeves and et al., who tested the virtual fence. But this is a really obvious oversight, and we really need to be testing the kinds of technology that's being developed. There are also contextual factors that affect the signal transmission, some of which were flagged in earlier talks. So the idea of topography, like the hills you're seeing in the image above, the curve in the road, the vegetation, the road material, so whether it's paved or it's gravel, will affect, particularly for sound, how much it's attenuated. So if you've got a gravel surface, the sound is going to be captured by the gravel, and it won't travel as far. These factors can affect the likelihood of the signal being received. So let's talk about the receiver. Now, the organisms with whom you're wanting to communicate is our receiver. And the biology and the habits of the receiver will affect whether this communication produces the desired outcome. So for an auditory signal, like that produced by the shrew and the virtual fence, it makes sense to investigate the target species hearing. So on the left, I'm showing an audiogram where we've got frequency along the x-axis, or the bottom, and we've got the, I can't see it from here. Thank you, sound pressure level along the y-axis, or the vertical axis there. Now we've got 3 different species, but I'm just going to focus on the wallaby diagram here. And you can see that the greatest sensitivity is actually where the graph comes down closest to the axis. So this means the lowest amount of sound pressure is required for them to actually hear it. Okay? So for the wallaby, that's between 8 and 12 kilohertz. And as soon as you go past that, it jumps up quite significantly. By 10 decibels, needs to be that much louder. And the decibel scale is a logarithmic scale, and that means for each 10 decibels, you need a tenfold greater increase. So you need, at 20 kilohertz, it's got to be 10 decibels louder. So shrew, when you look at the signal it produces, and this is a spectrogram of the signal produced by the shrew, it makes a number of pulses. So this is just one pulse. It gets repeated over and over and over again. It's approximately 1 second in length. It's very noisy signal, and it's very raspy in its character. But the dominant tone is this upper diagonal line that you're seeing, and it's going from 22 kilohertz to 17 kilohertz. And that means it's above that main sensitivity zone that is true for the wallabies. So you're getting a misalignment between what the signal's producing and what they can hear. It means it needs to have to be much louder in order for the wallaby to be able to hear it. Now, clearly, if you're wanting an animal to respond, you surely would want to try and target the frequencies where they hear the best. Now, I can't comment on the virtual fence in terms of these sorts of aspects because that data hasn't been made available and it hasn't been reported in any scientific trials. So, thinking about response. How your receiver responds gives you an insight into whether the signal has been received and if it has any meaning. So, playback behavior trials help to reveal this. If they keep feeding, they may not have received it. All the behaviors from there on, shown from 2 through to 8, tell you something about them probably receiving it, their interest, and a confirmation of that transmission. Now, caution is needed because a response may be elicited because the transmission is simply novel. Response may not last, however, when it's novel because animals become habituated, as has been discussed earlier. So it needs to be paired with something that's either positive and reinforcing or negative and reinforcing. So if the signal has meaning, however, like the eastern grey kangaroo alarm thump signal, which is given when there's a predator, ignoring such a signal can risk death. And so habituation tends to be low. How the target species responds and if that response is appropriate and the timeliness of that response is your next question from a biological and a behavioral targeting of that species. Now, Enma Lee in 2010 looked at red and eastern grey and Euros, and they comment that their flight pattern evolved to be unpredictable in direction along an erratic path to deal with high-level threats, making them more susceptible to being hit. And these tendencies tend to vary with day and night. So this certainly suggests that kangaroos generally, that technologies seeking to reduce wildlife vehicle collisions need to allow quite long response times in order for the animals to be able to clear the road before the vehicle comes through. So I want to emphasize that the elements of the transmission model and the considerations for each part of this model apply equally to communication between vehicles and humans, or between the vehicles, just those two, such as might occur with smart cars or GIS hotspot technology, which might modify driver behavior. And I'm going to hand over to Graham now to talk to you about design, monitoring, and analysis.
Right, imagine now that having been through the principles that Helen has outlined, we now have a product that appears to have potential to be applied in the wild. And I'm going to be talking about how to run field trials, how to design them, how to monitor them, and how to analyse them. And this will be a bit of Biology 101 as well, but we can't really help it because we're talking about wildlife. One of the big things that wildlife people have to face up to is the problem of variation. And variation occurs in 2 dimensions, time and place. And we've got variation, we all know about dawn and dusk, so there's daily variation in roadkill or WVC. There are lunar patterns, phases of the moon make a difference. Seasons make a difference, as we heard about with the koalas. And one year is not the same as the next. So we have an enormous variation, particularly in the Australian ecological context. And then spatially, we have very local fine-scale differences. Why were those 2 roos hit there rather than 10 metres further down the road? We have effects of habitat. Makes a big difference whether you've got appropriate habitat near the road or further away, for example. Home ranges, Ben talked about those, and even larger at a landscape scale, so the mosaic of landscapes that the wildlife is operating in. And all of that will influence the occurrence and the location of roadkill. And we need to think about that. So I'm going to look at a real-life situation. This is a stretch of the Northern Highway in central Victoria. On the bottom left, there's a little intersection called Ladies Pass. Over on the right-hand side, which is north, there's a little hamlet called Tuleen, and the stretch of road between them shows a fairly typical bit of landscape in Australia. Patches of bush, patches of farmland, and other bits and pieces, creeks and roads intersecting. And we'll look first of all at perhaps the simplest design, a before-after, And the advantage of a before-after is it uses the same place, so we know what we're talking about. And the disadvantage is that it occurs at two different times by definition. So here we are, we're looking at our before data. We've been monitoring this little stretch of road. We know it's a bad place. This is kangaroos in particular here, so that we get a lot of roadkill. So we think what we need is a tech solution. So here it is, glowing brilliantly. It's a wonderful answer to all our problems. This is the after. So we've monitored them before. We compare that with the rate after. There are multiple problems with this very simple design, and one that's been touched on is the novelty effect, whereas we get changes simply because this thing is new. So you need to look at it through time, because time is not being controlled. And time matters. This is the data from the Fox et al. Study in Tasmania, and it shows the virtual fence and the non-virtual fence control area roadkill rate. Just have a look at the early figures for February, March 2014. A year later, February, March 2015, regardless of whether the virtual fence was there or not, a huge difference in the roadkill rate. So it shows the effect of time, which, as I said, in this design wasn't controlled. The second approach is a control impact design. This one uses the same time, so you've controlled for that time problem, but you've got two different places. Right. So we've got our control here, further on the left, and the treatment there. And again, we have problems because we know that spatially there's going to be variation. These are some data on wombats, and you can see up the top of the road there's a lot more roadkill concentrated. Further south, there's much less. So depending on where you put your control and treatment areas, you can get very different outputs. The much stronger solution is a backy design, before-after control impact. And here we've got the before running all along that stretch of road, so we measure it before. Then we bring in our control and our impact, which is the after. And now we're interested in the difference between before control, the change in that, versus the change in before and impact. And that is a much stronger design, but it still has limitations, in particular because we're still only talking about one little bit of space. So then we get into what we really want is replication in time and place. This is more of a gold star approach. And here I've got 3 control sites, 3 impact sites. You can then get into more complex designs like crossover designs, where your controls later become impacts and your impacts become controls. You can randomise it, you can extend the replication, then you're getting somewhere. The next talk by Chris Connolly will show you a design like this, and you can see how it can be done well. I'm running out of time, so I won't say much about monitoring, except it has to be done well, and it's not easy. It's particularly for using citizen science, it needs a lot of coordination and curation. And finally, when you've got all this data, you'll need to analyse it. So here's some work on wombats from New South Wales. If you have a look at the impact figures, before there were 23 roadkills of wombats. After the treatment was used, this is a virtual fence, 6, looks fantastic. But if you look at the control, 64 down to 17, and when you apply a formal but very simple chi-square analysis, the expected frequencies are in those little numbers, and the answer from the analysis tells you that this result is completely due to chance. I could be 97% confident of that. Okay, so conclusions. There are two key stages in the process of developing a mitigation system. First of all, you need to go through solid product development, and as Helena explained, that rarely happens. Somebody comes up with a brain idea and then it just gets released without adequate understanding of what's going on. Second, you need to evaluate it properly, and to do that you need the sorts of designs I've been talking about. And then if you discover it didn't work, as we're now finding with the virtual fence, you don't have the first stage, understanding, to even know why it went wrong. So I'll leave it there. Thank you.
Thank you. Thanks. Yes, stay up, Graham. Come up, Helena. Great talk and great insights. 97% likely just by chance. It would be nice. Helena, you made a comment earlier about deciding on the noise and light stimuli after considering everything else. What do you mean by that?
I mean thinking about the receiver, the transmission, the message. You need to get the biology correct before you then start doing that technology. So getting the animal ability, particularly if you're using sound, to match up with whatever you're going to make needs to happen before you go into the detail of spending a lot of money on making that technology and doing all the sorts of trials that Graham was just saying, to be able to see whether, if you're going to put it on a vehicle, if you can actually hear it above the vehicle noise. All of that really needs to happen early on.
Yep. Great, thanks. There's a question that's asked a few times about don't brake or swerve for animals, and what does that mean? I'm going to hold that one over to the panel at the end of the day. Another issue for the Shuru and other vehicle-mounted things is the Doppler effect. What is that, and what is it? Why is it a problem?
Right. So the Doppler effect is describing what happens when a sound is traveling and it's hitting air and it compresses the sound, so it changes the frequency. And usually it's making it push up, so it goes initially higher and then lower than when it passes you. And you will have heard it when a ambulance goes past, so it sounds one way and then the sound changes when it goes past. That's what they're describing with this Doppler effect. So the sound that you design may not be the actual sound that gets experienced. And so part of it's about testing that in context to actually get the response.
And I guess, Graham, two quick ones for you. Studies on virtual fencing is very much infancy. Would you agree more research is required?
I would agree more research is required, but I think at least half of that research has to be directed to the stage 1 questions. So what are these things producing in terms of light and sound? Are they of any relevance or perception for the target species? What are the target species? There's probably no one size fits all. And when you've got a better handle on that, you might then do some more field trials. But I think the field trials, such as they are, have been far in advance of understanding what the devices actually do.